Understanding MAC addresses. What is a MAC address? A MAC address is a unique identifier assigned to a network interface controller for use as a network address in communications within a network segment, typically displayed as 6 groups of 2 hexadecimal digits separated by colons or hyphens. Each MAC address is supposed to be globally unique. Manufacturers assign MAC addresses to hardware, and the first part of the address identifies the manufacturer. It operates at the layer 2 of the data link layer of the OSI model, used for communication within a local network not routable across the whole internet. While they are generally unique, that doesn't mean you can't change them as you wish. There is even a format for random MAC addresses. These are used by smartphones for when they connect to Wi-Fi access points to prevent tracking of the phone by the Wi-Fi providing company. Also, MAC addresses only need to be unique within the local network. They don't conflict if they are on different network segments. It's an important point if you're changing a MAC. So what's MAC addresses used for? In this video, I've drawn up a simple example of a small network. We have a PC, a printer, a switch, and a router. You can see the IP addresses for the PC, the printer, and the router, and you can also see the MAC addresses for each of them. In order to send any data anywhere, the PC has to send it as a frame with the data inside. Frames are how communication happens at layer 2. Packets is how communication happens at layer 3. Frames use MAC addresses for source and destination addresses, and packets use IP addresses for source and destination address. So when the PC wants to send a packet, it breaks the packet down into frames. If the packet is for an IP address in the same subnet, so within this network, then it sends the frames directly to the other host. If the IP address lies outside of the local subnet, so it's not within this network, it sends the frames to its default gateway, the router here, so that it can forward them on. The PC doesn't need to be aware of how the general internet works, just needs to decide if it's local or not. Switches provide switching, which is the term used to describe switching frames between interfaces. A switch is not aware of an IP address, it's only aware of the MAC addresses. In order to be efficient, a switch maintains a MAC table. This lists the MAC addresses seen on each port, so that when it receives a frame, it knows from this table what port to forward the frame out on. So when it receives a packet from this PC, and this PC is trying to send it to the printer on this MAC address, it will send it out that port. It will not send it out the port to the router, it only sends out this port. It's very good for controlling capacity on links. Each switch has a limited MAC table. This is really important when selecting switches for the size of network you have. Most switches only support about 8,000 MAC entries, so that limits you to just below the capacity of a /19 network. Some switches have even lower than 8K, so you just need to be very careful when you're picking your switches depending on the size of your network. So let's say this PC wants to send a packet to the printer. It knows that its local LAN has a mask of 255.225.225.0, which can also be referred to as a /24. This means that given its IP address is .21 and they are on a /24, then the hosts that are local to it lie within the IP ranges of 192.168.0 to 0.254. 0.0 is a network address and can't be used, and 255 is a broadcast address and can't be used for hosts. So this PC wants to send a packet to .20, which lies within the range of IP addresses. Therefore, it can communicate directly with the printer. It doesn't need to talk with the router. Before it can send a frame, though, to this printer, it needs to know the destination MAC address. First, it will check the ARP table on the PC to see if it has a MAC address already for 192.168.0.20. If yes, then it will use that destination, and if not, it will have to figure it out. So it needs to find the MAC address for .20. To use this, it uses the ARP protocol. An ARP request is a packet stuffed into a frame and sent out to the broadcast MAC address of all Fs, asking who has the IP address. In this example, we are looking for 192.168.0.20. So you can see the source MAC address of this PC is sending it to the broadcast MAC address. When a switch receives a frame with destination MAC of broadcast, it will forward a copy of the frame out every interface. All devices listen to ARP requests and only reply if the request is for an IP address that is configured on it. If that is the case, it sends an ARP reply back to the source MAC address from where the ARP request came from. It doesn't send it back to the broadcast address. So in this case, we see the printer sending back the ARP reply with a source MAC address of itself and the destination MAC of our PC. As the destination MAC is specified, the switch only forwards the reply out one port, i.e. the router sees all ARP requests here, but it never sees ARP replies unless it's to itself. So therefore the router must learn its network through its own ARP requests. Yes, the bigger the network, the more ARP packets are flying around taking up capacity. Now that the PC has the destination MAC, it can construct a frame with the destination MAC and the printer info IP packet as the payload. The switch sends the packet directly to the printer, doesn't send it at every address because the destination MAC is defined and it has learned that that destination MAC is on that interface. Notice how all of this communication for the printing happened without a router or firewall seeing any of it. This is the basis for lateral movement by malware in a network and why port isolation is so important within networks. So what happens when you want to send a packet to someone outside their network? How do you find the destination MAC? Well, the answer is you don't need to know the destination MAC. That's not how it works. So if this PC here wants to send to the printer over here, the PC is aware that its IP address is 10.20 and it's aware that that 10.20 lies outside of its subnet. So in order to send anything to it, what it knows is that it can't send it locally, it has to send it to its default gateway, which is this interface here on its router. So because it's an IP address that lies outside of its subnet, it sends the packet in a frame to the default gateway. So the source MAC address for the frame is this address here, which is the PC's MAC address, and the destination MAC address is the MAC address for the default gateway. So 192.168.0.1, that MAC address is this one here. Now a router will have lots of MAC addresses. It will have a MAC address for each interface. So in this case, this is the MAC address. So the frame that's going to get sent from this PC through the switch to the router is going to have a source MAC of itself and a destination MAC of this router interface here. So from a layer 2 level, the communication is from here to here, nothing else. Not aware of anything higher than that. Now the router receives this frame, and in the frame it sees an IP packet. Now unlike the switch isn't aware of IP packets, it's just passing frames between the router and the PC, but a router is aware of IP addresses. So the router sees that in this IP packet, the PC wants to send a packet to 10.20. It doesn't necessarily know where 10.20 is. All it knows is that to get to 10.20, it has a route for it. It needs to send it to 5.2. It's one of the major principles of how routing works on the internet. The router just needs to know where is the next hop. It doesn't necessarily need to know the whole way there. It just needs to know the next hop. So what the router does is it builds a frame and pops the IP information into the frame. In this case, the frame will have a source MAC address of this interface here, which is also different from this one here, and it will have a destination MAC address of the 5.2, which is the next hop, which is this MAC here. So in this section here, the frame has a different source and destination address than you had in the frames here and here. So they're essentially completely different frames, apart from the payload data is the same. So frames have got it to here to the router, and from here, from this router to this router. Excuse me. Now there could be multiple switches along this route here. I haven't drawn them in. If there was, it would work in the same principle. The switch doesn't care about anything except the MAC addresses, and so we just forward it onto the router. So when the frame arrives at this router here, at the second router, it sees that it's connected to the required subnet 10.0. So it's not a route to the next hop. It knows it's connected to that network. So what it does, it sends out an ARP request to find out who .10.20 is. So similarly, as we showed earlier, it would send out an ARP, the switch would send it out all its interfaces, and the printer would reply telling the router what its MAC address is, which is here. The router then takes the IP payload from the PC, pops it into a frame, assigns to that frame a source MAC address of its interface here, and a destination MAC of this printer here. So from the point of view of the printer, the source IP address is 192.168.0.21, but the source MAC address is this value here. It is not the MAC address of the PC. Why does it work like this? In really brief reasons, without going into the whole reason the way the world global internet works, mainly because this scales globally. The PC doesn't need to know anything about the printer other than the IP address that gets it there. The local switch doesn't need to know anything where anything is. It just switches based on the MAC addresses in the frames. It isn't even aware of the IP addresses. It just sees the PC and router sending frames between each other. This allows switches to be made very dumb, which basically means they can be built fast and dumb, so they can do lots of stuff for cheap. The router doesn't need to know anything about the printer, just what interface to send out the packets and frames on. So it doesn't need to know that it hangs off any particular network. It just knows that for that network it sends it that way, out that interface. Again, this allows routers to be simplified down. If they don't need to know the whole global internet routing, they just need to know where to send next. And this is where the default route comes from. You can basically just say, okay, send everything out that port and the ISP will take care of it, allowing your router to be built cheaply. Each step along the way handles all the next hops. So the router to router communication, they do their bit. So this hides things like MTU technology, the global routing network, from the PC and from the printer. By keeping things simple, you can build tiny circuits. So tiny IoT devices, for example, can communicate with any IP address in the world. They don't need huge resources for processing packets. They basically just need to know how to send the packet locally with a frame, or send it as a frame to their local router, and now the rest of the world takes care of their packet for them. That's the basis of it. Thanks.